and your name and everything beforehand.
I'm Craig Tooley. I'm NASA's project manager for MMS. I'm from Goddard Space Flight Center, which is actually where we built the MMS spacecraft and will fly the mission from. This is an in-house NASA mission, so we are our own prime contractor. The instrument suite was led by Southwest Research Institute out of San Antonio, and there's actually behind me here, if you count them up, you would count 100 science instruments on those, altogether on those 4 observatories. And they were built by a variety of institutions. Southwest Research, Goddard Space Flight Center built some of them. A whole suite of them for the electric and magnetic fields were done by the University of New Hampshire. We also have an Austrian contribution, and we have some participation from the Swedes, and we have some Japanese participation. So it's a very broad, inclusive science group. What we do, and why we have 4 MMSs, is MMS is essentially a flying laboratory. It's not quite, it's better thought of as an in situ flying laboratory rather than a remote sensing mission. We fly these 4 out into our, through our own magnetic field around the Earth in a region first called the bow shock. It's called the bow shock because that's where the sun's interplanetary magnetic field essentially collides with and distorts our own planet's magnetic field. And as you probably know, it's really fortunate we have a magnetic field because that's what shields all of us on the planet from most of both the solar and galactic radiation that flows our way. Mars, for example, no longer has a magnetic field, a mystery of where it went. We believe it used to. But that, just having a magnetic field is fundamental to life on Earth. It protects us from what would be a very high level of radiation. But those interactions occur between the sun's magnetic field and the Earth's magnetic field, principally in an event called magnetic reconnection. And that's when the conditions are right for the field lines. The magnetic fields actually change their configuration. If you imagine little lines representing fields, as you often see in textbooks or something, you would actually see that we would represent it as those lines breaking, the ones from the Earth breaking and reconnecting differently with the ones from the sun. When that happens, an enormous amount of energy is pumped into accelerating and heating the plasma, the electrons, the protons, and some of the heavy ions that are continually flowing from the sun, and it pumps them into our own near space environment, essentially our space weather environment. It's the principal energy input into our space weather. It's a phenomenon that occurs on the surface of the sun. It causes solar flares when it happens on the sun itself. It happens in stars and in black hole accretion disks, we now understand. It happens on the ground in controlled fusion laboratories and disrupts their attempts to get controlled fusion. As a phenomenon, it's been recognized for probably only about 20 years as actually being a significant physical phenomenon. If you read back farther, you'd find the scientists arguing about its very existence. It's now understood to be a fundamental physical process that we don't understand very well. We certainly can't predict it very well. We can't write the equations with the right terms to say we know what causes it, we know what drives it, we know what triggers it. Understanding those things would be very important to understanding a whole host of phenomena. So we're going to fly a laboratory with 4 spacecraft as close as 10 kilometers together in a little tetrahedron shape so we can get 4 pieces of data in 3 dimensions. We do it very quickly because the magnetic reconnection event is less than a second. And it happens as close as 10 kilometers, maybe as far as 200 kilometers. So we're going to, in the first part of the mission, we're going to have to be fine-tuning how far apart we fly these 4 spacecraft to be the right scale for when we think we're catching these magnetic reconnection events. These are fairly large, but when we fly, we deploy 60-meter wire booms on 4 sides and 15-meter booms out axial direction, all while spinning at 3 RPM, all while flying with our propulsion system very precise orientation and very precise relation to each other. 60-meter on-side wire booms for scale. If you put an MMS deployed footprint down, it takes up a whole baseball field, including the outfield. That's what we're flying in precision. And of course the wire booms are flexible, so it's a very challenging flight dynamics mission.
So how long do you anticipate the mission to be?
The mission the prime mission is 2 years long, and that's driven by we fly out. We're in a highly elliptical orbit, which means our closest point, our perigee, is about 7,000 kilometers high. So not real high. But our apogee during the first year is 75,000 kilometers. And that basically is the distance out to this bow shot. So that orbit, as we go around the sun, we start out where the high point of the orbit's not in the bow shot. And then as months pass and we go around the sun, we sweep into that region. Before we get there, we're going to get this all commissioned and checked out. We enter that region, we sweep through it. That's our prime science in the first year. We go through that region looking for magnetic reconnection. We swing out, we will come back around one more time through that region. So we get 2 passes through what we call a region of interest or at the magnetoposit. Then for the second year, as we come around, we use this propulsion system. We double that distance to about 160,000 kilometers, which is just shy of halfway to the moon distance-wise. And then we look for magnetic reconnection because we know it also occurs in what's called the magnetotail. The Earth's magnetosphere, if you look at it, kind of looks like a tadpole. It's bunched up here, it's been kind of deformed. The sun has pushed it this way and it has a tail. And it's out in this, it's both up here at the front and then in the tail region where we know magnetic reconnection occurs. So in that second year, we'll swing that higher orbit through that tail and collect magnetic reconnection. Now, if we pass through that, we think we'll have collected enough magnetic reconnection events to essentially solve the problem of how does magnetic reconnection work. Scientists will be able to model it and understand what the conditions are from the electric fields, the magnetic fields, the plasma conditions that trigger it and drive it. That's our objective. We believe this will answer that definitively. So it's a 2-year mission. Now, NASA will have the prerogative and the option of flying it longer. We have enough fuel on board to fly at least 1 more, if not 2 more years, depending on how much precision we want to maintain that formation. We can let it string out, and then it doesn't take very much. But that'll all result in what makes sense to do with these after that 2 years.
Obviously, we've just had the Discover mission as well,
right,
which is looking at it from a different angle. Are you going to be able to link up the information coming through from Discover?
The subjects are very related, but there's the fundamental difference between MMS and Discover is Discover's space weather objective is Discover is essentially a space weather buoy, like you would have a buoy in the ocean. Its purpose is to simply detect oncoming events from the sun. So we have roughly an hour warning. It's far enough away at L1 that it'll say, the conditions from the magnetic fields and the particles are such that we see a solar event that's gonna hit our magnetosphere, and then that data is literally sent to power companies, power grids, so they can compare it. It's sent to satellite operators. It's sent to airlines. They reroute their flights over the poles because the radiation is too high. They will actually fly a different path so the flight can get better. So they're basically an operational, really, space weather satellite. MMS, on the other hand, is a fundamental physics satellite to understand what's behind some phenomena that drives space weather. But we're not an operational early warning. Now we collect similar data, but we're actually much closer than Discover to the Earth. So the subjects, when you talk about space weather related, we're a fundamental physics science mission. Discover is an operational NOAA mission actually to do weather, at least 1 hour weather prediction for space weather. As well as Discover, obviously, if you look at it, I won't go into it, carries some secondary instruments that do more science, but that's obviously a little farther afield than related to this.
So I guess one thing I was trying to clarify from my own understanding is the magnetic reconnection that you hope to or expect to observe, is that an influencer of space weather itself, or
yes,
is that just like a representative of the type of events we see come from the sun?
It's very much a driver of space weather in our own magnetosphere. So we'll have magnetic reconnection events, and then we will get geomagnetic storms. You will see much brighter auroras. You can trace it to magnetic reconnection events as energy is dumped into our near space environment. So it is a driver of the changes. Sometimes the changes we care about avoiding in our space weather environment.
So in other words, all these harmful effects that, again, we might have learned about in the context of Discover, they can happen from reconnection events that Discover would never see. They're much closer to Earth, or are they just not nearly as dangerous as the solar type events that were monitored?
The events that Discover people see. And Discover essentially detects events on the sun that are lined up in a way that the flux of plasma from either a solar flare or coronal mass ejection is going to run into this region where it will interact with our magnetosphere. That plasma in turn is the plasma that's involved in, is that going to trigger magnetic reconnection events that cause the effects of that plasma hitting our field. In other words, there's this thing coming from the sun, we know it's going to do something to us based on how big it is from Discovery, what class of coronal, how big a coronal mass ejection. Okay, when it reaches our near space, the effects then on the radiation environment and the changes in the magnetic field and the currents that flow in our, that's really one of the things that's most important. When this happens, we get essentially large electric currents flowing induced in our magnetosphere that induce currents and things on the ground. It's basically the effect of what Discover sees on us is governed by the transfer of the magnetic reconnection events that would trigger. We don't understand that very well. But we certainly know from Discover that if something's coming and it's large, we know from history what we've seen that that's something we should worry about to what degree. But what actually happens when it interacts with our environment specifically to cause that, that's not well understood, and that's where magnetic reconnection will play a key role in understanding just what happens when that stuff hits our magnetosphere, and why does it do this, and when would we be able to better understand and predict maybe what's going to happen.
So I don't want to belabor it, but I mean, so does it require a flare type event from the sun to trigger reconnection here, or it happens more sort of organically, if you will, anyway?
That is one of the questions: is just what are the conditions, the magnetics, electromagnetics, and the plasma that trigger it? We know that what exactly can trigger it. That is one of the questions. What are the initial conditions that can trigger this? And what scales does it happen on?
So what you can do is correlate the information you're getting from Discover in respect to the flare coming along.
We will watch the space weather
and see how that actually impacts upon the
I mean, just as important, it's important not to think of MMS. It's important not to think of MMS's purpose as being space weather. The physics we're investigating, we know are very important in space weather predictions, but the physics we're investigating are really fundamental physics. This fundamental phenomenon is not well understood. The only place we can actually measure it and explore it, turns out, the only laboratory we have is our own magnetosphere. But once we understand this, we'll understand better how solar flares are occurring, how the sun works. Why are we getting solar flares? What causes magnetic reconnection on the sun itself? What causes magnetic reconnection, in the accretion disks around neutron stars? And what is it? How will it affect when we're trying to create very complicated magnetic structures on Earth? Those people are very interested in magnetic reconnection also. So, as with all fundamental science, predicting exactly what the benefits will come from understanding science much better is hard to do.
When you talk about a connection event, and that burst of energy, is it a consistent amount of energy that's quantifiable like every time, or is it some are smaller, some are bigger?
I don't know the answer to that quantification. You have to remember, I'm an engineer, not a physicist. I'll give you the it's my mission. I understand
no problem.
The words could actually probably give you not a 101 but a higher level tutorial in magnetic reconnection. Because that is he and his heliophysics colleagues, that is what they're very focused on.
So MMS is basically finding out about the unknown.
Yes.
Right. So is one of the possibilities of harnessing the magnetic energy that's out there?
I don't think realistically we would
as far as examining that.
The one link to harnessing energy, though, is understanding magnetic reconnection may bring us closer to creating power positive controlled nuclear fusion on the ground and things. So the basic science might lead to benefits like that.
Right.
But harnessing it from the magnetosphere, I don't think so.
Ready whenever you are.
I'm Jim Birch. I'm from Southwest Research Institute in San Antonio, Texas. I'm a principal investigator of the magnetospheric multiscale mission, and our scientific objective is to understand magnetic reconnection. This is a phenomenon where if you have two magnetic fields that are in opposite directions, and there has to be a gas, an ionized gas there, pushing them together, something pushing them together, then you have an explosion in space. Magnetic energy is destroyed, explosively converted to particle energy and heat. This is why we have solar flares, why we have magnetic storms on Earth, why we have the aurora. It also occurs out in the outer part of space, astrophysical phenomena like supernovas, black holes. Reconnection plays an important role in these as well. It's also important in the laboratory, where we're trying to solve the energy crisis with controlled fusion. We can confine a plasma in a magnetic field, heat up the temperature to 100 million degrees, make fusion happen, but we can't sustain it. And the reason we can't sustain it is because magnetic reconnection sets in, allows the particles to escape. And so we're working with those people to relate what we learned to what they need to know, and hopefully we can help out.
How long have you been aware of the phenomenon?
This is a fairly new phenomenon. It was discovered by people looking at sunspots back in about 1947 and noticing that if two sunspots had opposite magnetic polarities, that's when you would have a flare. So somebody said, well, these magnetic fields must be reconnecting, causing this explosion. Well, so people in studying solar flares picked it up pretty quickly. As far as the Earth, when you talk about the aurora and magnetic storms, it's a very controversial topic for about 20 years. And, you know, it's gotten to the point now, I think there's only 2 people left who don't think it's the most important thing happening around the Earth. There's still always going to be 1 or 2 people who don't believe in it. But, and the same thing with astrophysics. It wasn't, magnetic fields weren't seen to be that important out in astrophysics where you're creating cosmic rays and supernovas and things. It was all gravity. But over the last 20 years, there's been a realization that magnetic fields are important there as well. And so it's gotten to the point now where it's seen by people in a lot of different fields. It's a very fundamentally important thing.
So you're saying
it'll happen within the last, say, 60 years.
So also you're saying that this is possibly going to have an impact upon clean energy with the fusion and stuff like that?
Well, you know, we hope so. We're talking to those people. They don't know why that reconnection sets in and causes their device to crash, and these sawtooth oscillations they call it. And so we work with them, but it could be something. I mean, we're looking at a lot of things here like heavy ions. It could be that a certain fraction of heavy ions like oxygen as compared to hydrogen, maybe it affects this rate of reconnection, and then it could be used to quench it. It could be certain waves that we see that are naturally occurring, and maybe when certain waves occur, radio waves, then the rate is reduced. Maybe that could quench it. If that's the case, then these people could inject those kind of waves into their device. So, you know, I'm sure there's something that quenches it. And if we can find out what that is, it will help the people doing control fusion.
Okay, thank you very much.
So you're going to be inserting radio waves into events as they happen?
I'm talking about in the laboratory. In space, we're at the mercy of space, so we measure whatever is there, but we do know there are a lot of wave phenomena. Another thing that they use to heat up plasmas in the laboratory are neutral particles that they inject. Well, in space, you know, most of the gas is ionized, but the fact is there's more neutral gas than there is ionized gas, even so. So there's a lot of neutral gas. So it could be, that could have an effect. But we're not measuring neutral gas, so we're not going to probably help right there, but that's something that could.
So what's the main hypothesis of the experiments that you want to run, or you want to get results from?
For this mission?
Yeah.
Well, all of the instruments work together to do one experiment, really. It's just all one big experiment. So to do it right, you have to measure all the electrons, all the ions, all the different species of ions, all the different waves, the electric fields and the magnetic fields, to a very high resolution. The time resolution of our electron measurements are 100 times faster than have ever been done before. in space. And so we realized we had to do that, so it was difficult. Our ion measurement is also about 100 times faster.
Is this an outgrowth of a decadal survey type?
Decadal survey of solar and space physics of 2003 rated this as the highest priority, call it moderate scale mission, which was still $1 billion. It was the highest priority in solar and space physics. That's why NASA immediately, had a competition right away. In 2003, we wrote our proposal. And, so
trying to wrap up, folks, as soon as you can.
And it's probably a silly question, but is reconnection seen as like a good thing or bad thing, or just something that happens? Is it a healthy process that needs to happen?
It's something that
something that we worry about because of all the damage that storms can cause and that kind of thing.
It can cause damage. On Earth, we have to protect systems when you know a storm is coming. So maybe what we do can help us predict great magnetic storms better, possibly. But that's not what we're doing. We're doing it to understand the process, why it happens, how it happens. We know where, when, not how and why. So it's part of the scientific process.
I mean, I guess what I'm trying to understand is that, it happens, but what are the consequences of it? I mean, again, I know space weather is one that we see here, but in general, what's affected terrestrially?